In this video, we are going to take a look at differentiating and integrating power series. Yay, we're finally getting into some calculus with this stuff now. So, power series can be differentiated or integrated term by term, just like we would differentiate or integrate a polynomial function term by term. And so that's what it is telling us in this box here. This is telling us that if we have a function that can be represented by a power series, and this power series is centered at A, that we can differentiate term by term. And so we have c sub 0 goes away, c sub 1 times x minus a just becomes c sub 1, and so c sub 2 times x minus a squared becomes 2 times c2 minus x minus a. And so we differentiate term by term. So let's take a look at the first example. So we have a power series. We have a function, first of all. Here's a function. And so we should be familiar with that function. That looks like a function that is somewhat similar to the sum of a geometric series. And we want to, oops, got a little thing there. Okay, we want to represent that with a power series. And so there is our power series representation of that function. First thing we need to do, if we're going to differentiate term by term, is we need to find all of the terms of this power series. Or not all of the terms, but the first few terms. And so that's what I'm doing here. I'm starting when n is equal to 0, n is equal to 1, 2, 3, 4, ... Then we simply differentiate term by term using the power rule. The most basic rule there is for finding a derivative. And when we do that, the derivative of 1 is 0. The derivative of negative 4x is negative 4. The derivative of 4 squared, now notice that I'm leaving it as 4 squared, not writing it as 16. That is, again, a useful thing to do when you are working with series. It helps sometimes to simplify it in the end. So we're going to have 4 squared times x squared becomes 2 times 4 squared to the n minus 1, or x. And so you can see term by term I have differentiated. Because now what we need to do, as always, is we need to come up with a formula for that. What is our power series formula, or just our power series, going to be? So here we have n equals 1, n equals 2, n equals 3, n equals 4. Now, why did I choose to start with n equals 1 rather than n equals 0? Sometimes it's arbitrary. You have to start with whatever value of n is going to make this a little bit easier, quite frankly. So it works out real nice if I let the n value agree with the power up here, and also agrees with this number out here. N equals 3 agrees with the power of 4, and that's so. Doing it that way, I say, well, I have a 4 to the n power. Get rid of some of this. I have a 4 to the n power. So here's a 4 to the n power, 4 to the n power, 4 to the n power. I have an x to the n minus 1 power, because if this is the n equals 2, I have 1 here, 3, I have 2, 4, I have 3, and then I have an n. n is 2, I got a 2, 3, I've got a 3, 4, I've got a 4. And then, of course, we have an alternating series. And so we want the first term to be negative. So if I start with n equals 1, and negative 1 to the 1 would be a negative. And so that will give me my alternating series starting with a negative, positive, negative, positive. And so here we have, this then is the derivative of the original power series. So it is somewhat of a laborious process. We have to find the power series term by term, differentiate term by term, and then create the power series for that differentiation. Well, integration is the same thing, and that's what this little box is basically telling us, is that we can integrate term by term. So let's just jump right into the example. So here we have a function, and it is being represented by this power series. And incidentally, you could go through with this power series, and we've done this before. We've created functions that represent the power series, and you could do that if you wanted to see that this function is equal to that power series. But that's not what we're aiming to do here right now. So what I want to do is I want to go through and find the first 4 or 5 terms. And so that's what I do here. Here's the term when n is equal to 0, when n is equal to 1, 2, 3, 4, dot, dot, dot. Then we are going to integrate using the power rule for integration. And so remember, the power rule for integration is x to the n plus 1 over n plus 1. And so 9x to the 8th becomes 9x to the 9th divided by 9, which is over here. Negative 9x to the 17th becomes negative 9x to the 18th divided by 18. So we're adding 1 to the power and then dividing by that. And so you can go through and you can see term by term that is what we are doing. All right, now comes the fun part. Well, before the fun part, we can do some canceling. 9 cancels with the 9. 9 cancels with the 18, with the 27, with the 36. So we get a little bit nicer looking function here. And so now we need to come up with the power series representation for that. Once again, if I start with n equals 1, then it makes it a little bit easier than n equals 0. But sometimes, well, you're going to see I've written it both ways. So we're starting positive, negative, positive, negative. So I want a negative 1 to the n plus 1 power. That way, when n is 1, we have a negative 1 to the second power, which will be positive. That'll give me a starting with a positive, then going to negative, positive, negative. And then here we have an x to the 9th power, which would be 9 times 1. The 18th power is 9 times 2, 9 times 3, 9 times 4. There's my pattern. So basically it is 9 times n. And then, of course, we are dividing by n. So there is my power series representation starting at n equals 1. Now, if I wanted to write that starting at n equals 0, we just have to figure out how to adjust the n's. So I'm going to leave that up to you. You could play with it, but here is what it would look like if we started it at n equals 0. And the only reason that I would want to start it at n equals 0 is because the original series started at n equals 0. It was easiest to figure it out starting with n equals 1. But now if you're going to start at n equals 0, you just have to adjust the n's a little bit. So that should be a nice little exercise for you to go through and go from this to this. All right, that's it. Differentiation integration, term by term for power series. See you in class.